of the Philosophical Society of Washington. Good evening. My name is John Ingersoll. I'm the president of the society, the oldest scientific society in Washington, D.C., 141 years old. The mission of the society is to provide a forum for discussion on the scientific topics of the day for all educated men and women. As you know, we are approaching the end of the fall season, 2012 fall season of the society's lectures, and we have today and one more left for this to the end of the year. The lectures in this session have covered a wide range of topics, from physics and astronomy to chemistry and biochemistry, to biotechnology and medicine, and to economics, which is the topic of this evening, and public policy. You can view the schedule of lectures, of previous lectures, and the future lectures at the website of the society at www.philsoc.org. I also like to remind you that starting about a year ago, we began to record all the lectures, and normally they're posted on the website within about 2 or 3 weeks after they get delivered here at the Cosmos Club. So if you like to go back and if you missed a lecture, like to go back and see a lecture you already watched, and like to listen to it again, you have the opportunity to do this now on a regular basis. This evening we welcome our members and guests to the lecture entitled Whole Brain Emulation: Envisioning Economies and Societies of Emulated Minds. The speaker is Robin Hanson, who is Associate Professor of Economics at George Mason University. Our order of business this evening is as follows. First, I will recognize the new members of the society. Then I will proceed having the recording secretary, Justin Steinmetz, read the minutes of the previous meeting. Then we will hear from our speaker, Robin Hanson. And then I will proceed with housekeeping announcements before we retire to the social hour. New members. I'm pleased this evening to welcome 4 new members to the society as follows. I'll mention their names. Alex Bailey, David Boyd, and Deborah Boyd. And all 3 have elected as regular members. Also, we have a 4th member who is the speaker. There's the tradition of the society to essentially elect the speaker as a regular member as well. And also that includes, of course, Professor Robin Hanson. So please join me in welcoming these 4 new members to the society as members. Next, our recording secretary, Justin Steinmetz, will read the minutes of our November 9 meeting. Justin.
President John Ingersoll called the 2,307th meeting to order at 8:06 p.m. November 9, 2012 in the Powell Auditorium of the Cosmos Club. Mr. Ingersoll announced the order of business and introduced 2 new members of the society, including the speaker of the evening. Mr. Ingersoll then introduced the speaker, Mr. Neil Gershenfeld of the Massachusetts Institute of Technology. Mr. Gershenfeld spoke on programming matter, the science of digital fabrication. Mr. Gershenfeld began by describing the science of fabrication as undergoing a movement, a form of revolution happening at maker fairs and hacker spaces, all centered around 3D printing and extending to the frontiers of manufacturing. He described how, in 1952, MIT connected a computer capable of real-time operation to a manufacturing machine for the first time, constructing aircraft parts. This created the context of digital manufacturing until now. Mr. Gershenfeld explained that the most advanced 3D printers still depend on the relevant information being stored in the controlling computer and not in the material. Any errors tend to accumulate, he said, because there's no notion of state in the material. Mr. Gershenfeld's research is focused towards putting information directly into the material instead of digitizing the overall design. Mr. Gershenfeld described common community fabrication labs, or Fab Labs, performing experimental manufacturing in the field based on an NSF community lab example. After interest in the research increased dramatically worldwide, it is now possible to start a Fab Lab that can construct almost anything for approximately $50,000 in equipment and $20,000 in raw materials, he said. An important future step for these labs is the ability to manufacture parts for the machines themselves, using the lab, thereby replicating the ability to manufacture. Mr. Gershenfeld explained that assembly of components is an appealing alternative to manufacturing processes, likening it to snapping together predefined functional Lego bricks. He gave an example of combining conductor and insulator bricks into complex circuits with many traces and layers, the machine acting as an assembler. Research is now focused on trying to make functional bricks smaller, enabling construction of integrated circuits. Mr. Gershenfeld noted that materials created with this discrete assembly method, such as carbon fiber composites where strength and weight are critical, can be higher performance than found using traditional manufacturing methods. Mr. Gershenfeld explained that for machines to take data and turn it into things, you also need methods to turn things into data. He described high-resolution scanners and advances in workflows to translate object descriptions into machine instructions. He noted that conventional engineering systems represent objects in ways burdened by legacy, and noted that there are now better modern ways to represent objects. His lab has developed a way to translate a 3D design into a one-dimensional code that later becomes the desired 3D shape, somewhat the opposite of protein folding. Each material joint knows only local information, but the entire sequence recreates the global shape. Mr. Gershenfeld described ambitious research based on growing chains of proteins with a method similar to solid phase synthesis, but are operating with orientations and attaching small collections of non-biological molecules. This will eventually enable printing with atomic precision by growing objects in a massively parallel process from an array of anchor beads, sending code into the material, causing them to organize into what you want to make. In a way, there is no manufacturing machine, he said. These materials are coded for their own construction. Mr. Gershenfeld noted that this research described will take approximately 20 years to finish, but the explicit goal is to make objects from the atomic level, similar to the fictional replicator in Star Trek. Mr. Gershenfeld made a detailed analogy between digital fabrication and the development of computers, noting the impact of parallel availability in both cases. Mainframes were expensive and had limited access, such as current fabrication research labs. But when computers became room-sized, their usage was defined by a workgroup instead of an organization, similar to modern fab labs. Machines that can make other machines are analogous to early hobbyist computers, such as the Altair, he said. Now inexpensive digital fabrication facilities are being created at a rate similar to the expansion of the early internet. Mr. Gershenfeld believes that microcontroller programming and 3D machining are means of personal expression that have never existed, but still touch something deep in our culture. Traditional manufacturing excels at mass-producing identical products, but digital fabrication can create products for a market of just one individual. The current stages of research form a hierarchy of functionality and cost, he said. Worldwide labs are globally connected with knowledge, but the skills and jobs to make things are still local. Instead of shipping products, they are made locally, suggesting an entirely new notion of economy that focuses around shipping data instead of shipping finished physical projects. Mr. Gershenfeld believes there is a precise parallel with software and music. A string of data can be a program or a sound, and now a thing. Mass manufacturing won't disappear, he feels, but it will be the least interesting form of manufacturing, as digital fabrication creates new market scales that are accessible to all. Mr. Gershenfeld found that children following along with the fab labs were so far ahead of local educational resources they needed additional assistance. Therefore, he helped start a project called the Fab Academy, where students have peers and work groups provided with mentors who are then linked globally. He noted that traditional education assumes scarcity that does not exist anymore, such as classroom space and physical books. Distance education is a good step, he said, but students are still connected to the educational equivalent of a mainframe computer. The Fab Academy is more like the internet, distributed educational nodes that are linked together. Digital communication challenges the scarcity of people and information, allowing the campus to come to the students with a bootstrapped set of tools. Mr. Gershenfeld believes that there is a growing accessibility of advanced research education being made dramatically more accessible to inventive people everywhere. He hopes ultimately to reach a much larger fraction of the world's brainpower by providing the appropriate tools to learn and create. With that, he closed his talk, and Mr. Ingersoll invited questions. So when asked about intellectual property concerns, Mr. Gershenfeld believes that intellectual property is only of value if there is a barrier to infringement and if infringement can be identified. He believes that traditional means of intellectual property protection are insufficient and that better ways to buy and sell to better fit this new reality will have to be developed. After the question and answer period, Mr. Ingersoll thanked the speaker, made the usual housekeeping announcements, and invited guests to apply for membership. At 9:34 p.m., President John Ingersoll adjourned the 2,307th meeting to the social hour. Attendance 85, weather clear, temperature 8 degrees Celsius. Respectfully submitted, Justin Simons, Recording Secretary.
Thank you, Justin. Any corrections to the meetings, to the minutes, rather? If there are no corrections, I'd like a motion member to approve them. Give a second. All in favor? Any opposed? The minutes are approved. Thank you, Justin. Before I proceed to introduce the speaker and the lecture, I'd like to mention that this evening's event is sponsored by the Policy Studies Organization. Today was the DuPont Summit. Members of society are allowed free of charge or to participate in that event. It's a whole-day event, once every year. And I'd like to thank the president, Paul Rich. Where are you? Can you stand up, please, to be recognized? Thank you. So now to the main event of this evening, the lecture on whole brain emulation, envisioning economies and societies of emulated minds, by Robin Hanson, who, as I mentioned, is a professor, associate professor of economics at George Mason University. I will say a few things about the lecture and introduce the speaker. According to the speaker this evening, the three most disruptive transactions in history were the introduction of humans, I guess us, I suppose, farming and industry. Moreover, the speaker guesses that if another transition lies ahead, its source is artificial intelligence in the form of whole brain emulations, or EMS for short, to occur sometime in about a century from now, or within the next century. The speaker applies standard social science to this unusual situation to outline a relatively likely reference scenario set modestly far into a post-EM transition world. He considers families, reproduction, life plans, daily activities, inequality, class, work training, property rights, firm management, industrial organization, urban agglomeration, security politics, and governance, to mention a few items in his formulation of EMS. So I'll leave the thunder to this. I don't want to say any more about the speech, so looking forward to your discussion of this fascinating subject. Robin Hanson is an associate professor of economics at George Mason University, as I already mentioned. He's also a research associate at the Future of Humanity Institute at Oxford University, and he's the chief scientist at Consensus Point. Robin received a master's in physics and a master's in the philosophy of science from the University of Chicago in 1984. For the next 9 years, he spent time researching artificial intelligence, Bayesian statistics, and hypertext publishing in a number of organizations, including Lockheed and NASA, and also on his own. He then went on to receive his PhD in social science at Caltech in 1997. From there, Robin moved to Berkeley, UC Berkeley, where he was a Robert Wood Johnson Foundation Health Policy Scholar. And from there, he moved to George Mason University more recently. Robin has written extensively and has a number of over 70 publications, author over 70 publications, and he has pioneered a number of avant-garde, I would say, subjects as prediction markets, also known as information markets or idea futures, since 1988. Robin has also developed new technologies for conditional, combinatorial, and intermediated trading. I guess a mouthful. Robin has also diverse research interests that include, among others, evolutionary psychology and bioethics of healthcare, application of game theory in a variety of situations, the survival of humanity, very long-term economic growth, machine intelligence, and interstellar colonization, among other things. So please join me in welcoming Professor Hanson to give his lecture on whole brain emulation and visioning economies and societies of emulated minds. Robin?
Thanks. Thanks. This should be fun. This is the recent history of economic growth in the United States. You may notice that quarter growth was up a little just before the election, and that may have helped turn the election. You also may have noticed 4 years ago there was a big downturn. You may have heard about that. This is the sort of thing that shows up in the news. This is the economic world of the big picture over the economy of the last few years. I want to say this is not the big picture. This is a bigger picture. The entire world over the last 60 years. And when you look at it that way, this is on a log graph, so this is a factor of 10 for each of these bars. An exponential growth looks like a line on a log growth, and that's nearly a line. The world economy has grown steadily, exponentially over the last half century. That's the big news. All the little fluctuations are small news compared to the big news that we've had relatively steady growth for a long time. But we can look farther back. If we go back 2,000 years, well, it's no longer a line. It was a line here for the last century or so, but then it looks like there was no growth. And then finally we have growth, and the big history story is growth suddenly started. This is called the Industrial Revolution. That's a bigger picture, worth more pondering than the recent fluctuations in GDP, or even the recent downturn in the United States. But if we go on a bigger time scale, if we go back 10,000 years, 12,000 years actually, then what we see that looked like a flat line is really as a line. It's really exponential growth over the last 5,000 years. It's just slower exponential growth, but it's still exponential. And then we move to a much faster rate of exponential growth. And before then it was flat, except, well, it wasn't. There was also, I mean, the data is poor, of course, but it also looks like exponential growth for a long time before that. And so these transitions between exponential modes, I will call singularities. I don't really care what you call them, but the key point is to think about history as a sequence of modes where in each mode, growth was exponential, and then there were these transitions between modes when things grew faster. We can take the model that fits this, and we can actually think about this on a growth rate chart as a function of time. So now I've got an exponential both ways, and this is years before 2050, which is an arbitrary date, just so that it all fits. And the point is you have relatively steady economic growth, the growth in the number of hunters, and then a transition to a farming phase where there was relatively steady growth in the number of farmers, and then a transition to the Industrial Revolution, where a transition to a modern economy where there is a much faster growth, exponential growth in the world economy. And if you go back farther, you can even look at, there's a growth rate at which brains grow from the very first animals 500 million years ago until humans, and you can see this as increasing growth rates. And looking at it this way raises the obvious question, could this happen again? Now the usual debate about the future of growth is, can the current rates of growth continue or must they eventually decline? But you could also ask the question, well, could they grow faster? Could you again have a faster growth rate following the sequence? So if we take these modes, we take their statistics, we have a doubling time for each one, roughly. Then we can say a doubling time factor, how much did doubling time increase? And we've got a remarkably consistent range of doubling time increases, and we can look at how big the mode grew, and that was also within a reasonable set of ranges. We can use those and we can say, well, if the next mode had statistics relative to this mode, similar to the way the previous modes have had statistics relative to the previous ones in terms of the amount by which growth increased, or the time duration, the amount of growth that happened before a new growth mode show up, and you put in those and you try to get numbers, you get numbers in this sort of range. From numbers that have already passed to numbers, well, a century from now. So in terms of when this would happen again, just looking purely at statistics, you've got any time in the next century, not very precise. When you look at how much faster would the new growth grow, you get a remarkably consistent prediction. 3 different projections based on the 3 different previous modes still all give you 1 to 2 week doubling time. I'll say that again. Projection based on previous statistics, merely projecting previous trends, would suggest sometime in the next century, you'd have a transition to a new economic growth mode where the economy doubles, not roughly every 15 years like it does now, but every week or 2. A really big change, any way you count it. What would that look like? If the transition were the similar sort of shape in terms of a power law like the last transition was, which was the smoothest of the ones we've seen, at least in terms of the data, it would look something like this. The world economy would grow roughly every 6% every few years, although it fluctuates by, say, 0.5% or 1%, so there'd be noise fluctuating around, you wouldn't notice. Then there'd be this underlying improvement of 0.5%, but you wouldn't see that in the noise. Then a 2% improvement over the usual. That would be an outlier. You'd say, wow, the world economy grew 2% faster than it usually does. And then it would be 14, 40, 150, 500. It would go way off the charts. I wrote this sort of analysis before the dot-com boom, and people ask me, is the dot-com boom this? And I say, no, not remotely close. You have to have a much bigger set of growth to be anything like what this is predicting, because this is huge. So that was all just purely numerology. We took previous statistics of what's happened so far. We don't have very many data points. We said, what if the next transition were like the last ones? And now we might ask, well, is that even possible? I mean, what could cause something like that, really? And we might look at the kinds of things people have talked about as science fiction projections of what could happen in the future and ask, are any of these things remotely, plausibly, the kind of thing that could make this kind of transition? Is it even in the ballpark? And the problem is, for most of it, no. I mean, space is big and it's wonderful, but it's just really slow. It takes a long time to get up there and back and to do things up there. It's hard to have a world economy doubling every week based on space exploration. It's also hard to do it based on new energy sources, because it turns out we only spend a tiny fraction of our economy on energy. Cheaper energy would be great, and we do a lot with it, but it's really hard to see how that would make the world economy grow a lot faster, as I'll show. Even something like nanotech is hard to tell the story. Maybe robots, as we'll see. One way to think about this, if we look at the world economy or the US economy in terms of different shares, something that's a very small share, like mining, raw materials, like the raw stuff they have in space, or even energy, those are a very small fraction of the economy, so even if you improve them a lot, it's really hard to make a big impact on the overall economy. If you made the best toothbrush ever, it was the most fantastic best toothbrush you'd ever seen, it would not make the world economy double every 2 weeks. Because toothbrushes just don't matter that much. You need something that matters a lot, that has a big impact. Let's slice things a different way. When we think about where all the money goes, most of it goes to people doing work. Split in the form of their willingness to spend time and into their willingness to be trained and to learn things. And that takes up 2/3 of income. If you could find a way to make this cheaper, now you've got something. Now you've got a way to make a big impact on the world economy, because we spend a lot on that. So I'm led to think about scenarios where we find a way to replace that or make it cheaper, and that's thought of in terms of artificial intelligence or robotics. And I'm going to focus on a particular scenario that I think is the most likely way to produce artificial intelligence on the scale of a century or so. We need 3 things to make this work. We need a lot of cheap computers. Computers are getting cheaper, but they're not cheap enough yet, and we'll talk about that. Parallel. We need to be able to take a brain and scan it in fine spatial and chemical resolution. We are actually pretty far along the way there, although, as I was saying, we don't know exactly what to be scanning for yet. And then we need models of how individual brain cells work, input-output models, that say, when we have this input and we have this internal state, this is the output and this is how the internal state changes. We have many models like that for many kinds of brain cells, but we need them for all the different kinds of brain cells, because the whole point is we're going to scan an individual person's brain, and then we're going to make a model of that brain in the computer where we map each cell that we see and we make a computer model of that cell. And then if we've got it right, if we've got enough detail, close enough, then when we turn on this model, it will have the same overall input-output behavior as the original brain. That's what it would mean to be a good enough model. And if you have the same input-output behavior, that means you could talk to it. It would talk back the same way the original person. It would remember things and talk about what it remembered. You could try to convince it to do a task for you, perhaps by offering to pay it or praise it, and it might do things for you. And that would be really economically valuable. And that's the scenario that I'm going to focus on in this talk. I'll say a little bit about some of the technical details. There are many depths at which you could emulate. That is, the brain is an incredibly complicated, detailed physical machine. And the question is, how deep do we need to go to simulate all the detail? How much of the detail really matters from the point of view of the overall input-output behavior? The brain is a biological device, and most of the biological functioning isn't necessary for the signaling that goes on, but we don't know exactly which. So a whole brain emulation roadmap was constructed 4 years ago, where they analyzed the different possible levels at which you could simulate things. They did rough estimates of how much computation it would take to simulate at that level. Then they projected Moore's law from the last 50 years into the future, and they made estimates of roughly when you could, for $1 million, make a device that could emulate a brain at that level of detail. And that gives us these dates as we go down. So just having sets of neurons doesn't take as much work as modeling each neuron, which takes less work than modeling all the compartments of the neurons, or all the different transmitters and metabolites in them, or even go details, etc. And as you can see, the time goes farther into the future when, for $1 million, you could do that. We can put this on a time chart this way, and we can say, these are these time charts for when, for $1 million, you could have a device that simulated the brain at that level. Of course, you might not get it right. That would be making certain assumptions, and you might be making the wrong assumptions. Now, for $1 billion, you can do it 11 years earlier, because computers are improving that fast. And so the scenario would be, people, as we get more and more computing power, we can model these things at smaller and smaller levels, and eventually we reach the point where we find that we model it with that much level of detail, it's good enough. We get the same basic input-output behavior as the original brain when we've got enough detail, and then we get some sort of a takeoff where we say, okay, this works, and now we can start to throw things away until we see what's the minimum thing that works, and that will presumably be less, and now we've got something that works at a certain level. So this would be an optimistic scenario, which is this is the only level of detail you need. More pessimistic scenario might be like down here, where you have to go all the way down to this level to get this model right, and then once you've got a model, you can throw some things away, but you can't throw very many things away until it works. But even here is mid-century. Mid-century, when you're at the point where you have enough computing power to do this, do a brute force model, find that it works, and then throw things away and see what you can get away with. Okay, so this is as much as I'm going to tell you about the technology of whole brain emulation. I am an economist. Many people have written lots of analyses of the technology of brain emulation, brain science, computer science, philosophers even about whether they have the same identity as you. That's all fascinating, but what I think is neglected is what I'm going to tell you about, which is to say, if there were actually these things in the world, what would the world then be like? I'm a social scientist. I used to be a physicist, and as a physicist, I was told, and I accepted that, of course, there was no such thing as social science. Those guys didn't know anything. They all just made it up. But when I got a PhD in economics, I decided that was wrong. We actually do know a lot of things, and I've learned a lot over the years. So I want to take what I know and apply it here. I am trying not to be creative or original, other than choosing this question. I intend for everything else I say to be the sort of thing other social scientists, if they thought about it, would agree largely with it, as roughly the things we know about social science applied to this unusual circumstance. I'm just going to try to apply what we know here. Many people have written science fiction stories about whole brain emulations, describing how they would make an adventure story or an exciting conflict. Those are also not my agenda. I want to know what the world would really be like. Not what a great story would be like, but what the actual mundane lives. Just like your lives are different than the stories people told about the 2010, a century ago. They told much more interesting, entertaining stories, sorry. But you are real people. You exist in a real world that's important to understand for yourselves, and I want to understand how our real descendants would be like. So to simplify my analysis, to make it tractable, I'm going to make a number of assumptions. First, I'm going to focus on an era early enough that you can make an emulation, but you don't really understand. You can't take it apart into pieces and remap them and do things like that. You just have this emulation, and you can either turn it on or turn it off or something like that. You can make them faster or slower, but you can't like take one part of one guy and one part of another and mix them together, or just take out the music part and run the music part or something like that. You just have to take the whole thing. Next, I'm going to say this. I'm not going to predict the entire future. I'm going to predict the next era, because the next era will be the best basis for predicting whatever happens after that. I'm not saying this is the only thing that will ever happen. I'm saying this would be a plausible next thing to think about. I'm an economist, and economists have a standard set of assumptions that we use to do analysis to make it tractable. We typically look first at what's called supply and demand analysis, by which we mean a low regulation, competitive scenario. Lots of different actors competing, no one has very much market power, and largely free to do things as they want. I'm not saying there should not be regulation or that there will not be regulation. I'm saying that's the standard place we start with in doing an analysis, and then we do a differential to say how would it be different if we regulate. And in addition, I'm not going to focus on the transition phase, how it looks initially as these things show up and they start displacing people and people have problems, etc. I'm looking at what we might call an equilibrium, more of a steady state once this is the world, and the old world is largely gone and past, and this is the main new world and what's happening. So I'm focused on this world from their point of view in some sort of a initial, early, steady system. All right? So I'm going to organize some of the things I say initially in terms of the kinds of assumptions you need to draw the conclusions I'm going to draw. For some of the conclusions I draw, all you need to know is that the future is big. And it's bigger than we are. So a bigger economy in the future has a number of straightforward predictions. A bigger economy in the future will have basically better technology. It will be better able to do many things, including organizations. So they'll have better organizational technologies and contracts, which makes organizations bigger. There'll be more specialization, more niches, more kinds of music, more kinds of movies, etc. There'll be, of course, things that have a fixed cost, and then you can spread them across everybody, and there'll just be lots more of that, like music and stories, etc. There'll be more inequality. You can just guarantee that the difference between the biggest and the smallest of whatever it is will be more in a world that's bigger. But let's focus on the scenario where there are robots in the future. Robots are some way in which you embody what is valuable about a person in a machine instead. And I'm going to focus more on emulation in a moment. So one of the most obvious things is that machines can be immortal, at least when you embody information in them, because you can transfer the information from one machine to another. So you have a hard disk on a computer, you can transfer the information to another hard disk. If the first hard disk dies, you're transferring, in principle, immortality. That doesn't mean they have actual immortality, because you have to pay money to keep doing this transferring, and they might not have enough. But in principle, immortality is one basic feature of a world of robots. A world of robots can be immortal. Another basic feature is travel becomes easier, because if you are encoded in bits, then to travel to a faraway date, you just need to send the bits there and download them into another body somewhere else. You don't actually have to send the body. You might be worried about people stealing the bits along the way, but other than that, travel becomes easier. Another thing about a world of robots is that they don't care as much about nature. Now, you like nature, but in addition to liking nature, you are afraid that if nature dies, you will die, which is a perfectly reasonable fear, which is one of the reasons you don't want to kill nature. Good plan. Robots, however, can kill nature and not die, because they are not directly dependent on nature. They do not have natural bodies that need to interact with the rest of nature. They are made in factories, etc. They do not need nature, so they might or might not treat it more roughly. But the biggest thing that happens in a world of robots is that they can make copies of themselves easily. So for us, in order to make a useful trained adult, we have to start with a child and teach it all the way up. And to get another one, we have to start with another child and grow it all the way up. But once you can make copies, you just have one child and grow it up, or you just train one thing and then you make lots of copies, which is the usual economics of music and movies, etc., which is different than a performance. People who perform music is a different sort of scenario than doing one best performance and then making millions of copies of it. So we'll have a lot more focus on a small number of training and then lots of copies. A population explosion becomes possible, as I'll explain in a moment. And world economy can grow much faster than our economy does. So in our economy, we're limited by the fact that we can make machines very fast and we can make lots of them, but giving one person 1,000 machines isn't that much more useful than giving them 100 machines. There's diminishing returns. But once you can make 1,000 people and 1,000 machines, you can make substitutes for people, then the economy can grow a lot faster. And that's why a growth doubling time of a week or two is not at all crazy once you take into account the other things we know about economic growth, that in fact, a world where you can make substitutes for people straight out of a factory can grow very fast. And another straightforward implication is if you have this huge population explosion, wages have to fall to the cost of replacing one of the workers, which then falls to the cost of making this hardware, which then becomes very cheap. So wages fall and it's very hard to stop that. I can tell you in ordinary supply and demand terms, basically there's a demand for labor. There are things we can usefully do with labor. At the moment with human workers, the human supply is what's called inelastic. There's just a fixed supply for the most part. But when we replace humans with machines, then we have a very elastic supply because machines tend to have a very elastic supply of hardware. So the price falls dramatically, and even taking into account that you have a much bigger demand now because the world economy is richer, you still have a much lower wage. What about humans? Humans are eclipsed. They are pushed to the periphery. They are not the center of attention. If they were relying on their ability to earn wages and competing with the robots, they're in trouble. But they could have owned any small fraction of the new economy, stock, real estate, patents, or something. They can then be rich. They can use that wealth to be very comfortable, but not in the middle of things. They can't afford the expensive real estate where the center of other actions are, but they can be comfortable off in the periphery. Many people like to imagine a dramatic war between the robots and humans, but that's certainly not necessary. We can imagine humans more like the retirees of the new world. At the moment, we've got a lot of retirees who aren't productive in our society. We could say, well, let's all kill them and take their stuff. They're not actually helping, are they, right? But we don't do that because we would disrupt our economic system by doing that. There's not that much to be gained. Similarly, if the humans are a tiny fraction, they're integrated in the rest of the economy and the rest of the property rights, etc., there's not much reason to expect a drastic genocide. They can be the retirees of the new world. Emulations, which I'm calling M's for short, feel human in many ways. Remember, they once were human. They remember being human. They have all the usual humans' emotions and styles. They fall in love, they gossip, they argue. They have all the human personalities, except they are not representative sample of humans. They are selected. to be the humans who are most appropriate for this new world, who are the most well adapted to this world, in which case they will be different systematically. They may be smarter, more conscientious, more hardworking, or whatever the first ones who are in, if there are first mover gains. There are probably a few kids because there's not that much point of scanning in a kid and training it when you can take in adults and make lots of copies of adults who are more easily trained. And because you've got this huge selection effect of taking 7 billion humans and finding the few M's that are the most productive in this new world, there may be only a few hundred or even less humans that dominate, whose copies of them dominate this new world. It might be more like the forager society of sociology, or your distant ancestors only ever met 150 or so people in their entire life. They knew all of those people very well. It could be more like that. You're in a meeting and George is across the table. You know George very well. You know the sort of things he likes and he doesn't like. Well, you don't know this George because there's a trillion Georges, but you know what George is like so you can know how to deal with him. Be that sort of world of sociality. Humans may think these things are conscious or not. It doesn't really matter. Very few people might be willing to do it. That hardly matters. What matters is as long as a few people do it, there's a huge economic niche for them to fill. The question is what gets filled there. So emulations are different in some important ways. Just like you and your lives are more alienated from your natural source of being a forager, farmers are also more alienated, but you are more alienated than farmers in some sense, and they would be more alienated than you are. But humans seem to be pretty flexible and capable of being alienated and still function, even being happy, so that's probably okay. There's more ways to do loyalty tests on things, because you can actually look inside their brain and see what happens when you tell them things. You can put them in simulated scenarios they don't know are simulated and test what they do there. There's lots of ways to check their loyalty in those ways. Most leisure and most work would presumably be done in a virtual reality. There's not much point if they're mostly doing a desk job, you know, writing reports, designing things. They might as well be in a comfortable office from their subjective point of view because that's whatever it is that makes them most productive at their job. Similarly, they might as well have leisure in a nice world that looks nice and feels nice, as long as it's there. And so that means, in those senses, they could have a very nice life. They don't need to brush their teeth necessarily or clean things a lot, et cetera. There's no necessarily need to simulate all that stuff. Why not simulate a world that's easy and nice? Their bodies could be a wide range of kinds of bodies. When they did actual physical work, because there would be physical work to do, and many of them would be doing physical work, cleaning gutters or building buildings or changing production lines, et cetera. But one of the big things that is important to notice about how they can vary is they can vary in different speeds. So just once you have a computer program, you can run it at many different speeds depending on the speed of the hardware. So these emulations could be run at a variety of speeds, and that will have a variety of implications. And because brains are so parallel, and because the actual rate at which our brain cells fire is so much smaller than the rate at which we can make electronics trigger, it seems plausible that the cost to make an emulation will be linear in the speed up until, say, 10 million times faster than humans. So basically, you can make one fast or slow. If you make one 10 times faster, it'll cost 10 times as much to make it, and so you'll have to ask, are you getting 10 times the value from that one or not, if you're trying to get something useful done for them. All right, so let's think about some of the things we can do with this variety of speed. In the modern world, we have hierarchical organizations that are one of our fundamental ways that we organize activities. And they have a big limitation in that the top of the hierarchy is a communication bottleneck. It's hard to get a lot of things through that bottleneck. But that's where the bottleneck is, and so a lot of things just don't happen. You have to tell the boss, etc. So this is an example of a hierarchy. Each 4 people have a boss, each 4 bosses have another boss, etc. 5 levels for a total of 341 employees. What we can do if some of them can be faster than others, we can take the top 21 of them and make them all one guy running 21 times faster, who doesn't have to take meetings with himself. He can just meet with all these people below him and then coordinate his own activities in his head. He has to transition between tasks somewhat, which is a bit of a cost, but still doing those less meetings is a big advantage. The subordinates, of course, to meet with them, they'll have to temporarily go faster. So when you meet with the boss, you're temporarily faster and temporarily fast hardware, and then after the meeting, you're maybe slow again and go on to your usual things. And that's the way these M organizations could be much larger and better coordinated than a lot of human organizations by just cutting out the bottleneck of communication by having some things just run faster. Fast bosses. So let's think about the various classes of speed we might have. So one thing to realize is if they can run at many different speeds, they will run at many different speeds, but there's also the advantage of running at the same speeds as the other ones you're interacting with. It's awkward to talk with somebody who runs twice as fast or 3 times as fast as you, so they would probably clump in speeds. So here I'm going to assume they clump in factors of 16. So first of all, let's imagine ones that are at human speed. Initially, there'd be a bunch of those that interact with humans. And they would so also it turns out that our body has the natural frequencies of motion that roughly match the reaction time in our brain. There wasn't any point in having our brains react faster than the minimum time which we can change body parts, which is roughly 1/10 of a second. So as we make these things faster, if they were going to have a physical body that they interacted with naturally, it would have to be proportionally smaller. So a 16 times faster emulation would then have a 16 times smaller body that might comfortably use this truck at this point, because that's a 16 times smaller truck. And for them, going 16 times faster, then a year would be over for them, and what it would to us be 22 days. 256 times faster, well, they would be, if they had a naturally sized body, it would match the smallest standard railroad size model here, the little tiny figures staying on those fingers. And that for them, a year would be over in 34 hours. We can continue on. Another factor of 16. Well, now for these, a year is over in 2 hours. And for them, this foot is roughly the size of what an ordinary person would look like relative to their small bodies if they had a small body to match their speed. So we can continue on, of course, on to ridiculous heights of getting faster and faster and things happening smaller and smaller times until, of course, we reach the peak in social class of going in the other direction. It makes more sense to, if you're managing a physical system that's really small and tiny, like a nanotech factory, you need to be fast to manage the physical system. If you're managing a slow system, then you can be slow. Like if you're driving a supertanker, there's not that much point in having fast reactions. And so you can be a very slow thing. And in addition, these things, when they're no longer useful, instead of dying, you can retire them cheaply by slowing them down. So if you run it 1,000 times slower, then it only costs 1,000th as much, and so you can retire into slowness at a relatively slow cost. So look forward to slow retirement, and then the world speeds ahead, and you get to see lots of the future in your retirement. It's also, notice that as we go up this hierarchy, what will turn out is they will tend to be older, things with more subjective experience. They will be richer, because they just embody more wealth. They will tend to be bosses. They will be at premium locations, as we're going to see in a minute. They will tend to host meetings, as we saw. The world will be stable, etc. All of these are markers of high class and status. So faster is high class. It seems pretty obvious that they will be seen as higher status and higher class. There'll be basically separation of classes into high and low classes, based basically on their speed. There are many different tasks, and so again, we would want to allocate, they would be allocated to tasks based on speed. That is, you would set them to have a speed that matched the task. So again, managing a physical system, well, physical systems have a natural speed at which that you want to react to them, then you'd want an emulation at that speed. Bosses would want to be fast in general. It's also be handy to have leisure fast, because if you're on a job and then you stop doing the job, the rest of the people who count on you might like you to be back in 5 minutes. And you can be back in 5 minutes and have a whole day's worth of rest if you just have your leisure at a faster speed. So then it makes sense to just do leisure at a faster speed. If you want something, however, that remembers a long history, that has a long back memory, that you want something slow, something that interacts with humans would be slow, and of course something that retires would be slow. Another thing to think about is, because there's a certain growth rate of the economy, how fast the world will seem to change will depend on how fast you are. So for the very fastest emulations, most of the world around them is like the mountains that just can't change and don't change, and they have to take them as given and doing the small, fast things that they can do. Whereas at the other extreme, it's like being in at a cloud of noisy, busy insects. You'll just want to stay away from that cloud unless you are safe somehow, because the fast things are all noisy, busy, doing something that you can't watch and you're out of your control. And so whether the world seems fast or slow would depend on how fast you are. It's not a matter of intrinsically a fast or a slow world, but who is reacting to the world. Okay. Another key feature about speed is that there's a finite speed of light, and if in order to interact with you naturally, the longer the delay is, the less natural it is to interact with you. So if I want to interact with you in a virtual reality, you can actually be housed, your brain can be housed anywhere far away, as long as the time to send light to this between us is small enough that we don't notice the difference. So for humans at the moment, that distance is actually bigger than the radius of the Earth, or the circumference of the Earth. So we can have people spread all across the world, Earth in virtual realities interacting and not really notice how far apart they are. But as they get faster, that's no longer true. So if we move up by So as we move up a factor of 16, for example, for us it's the entire work, but a factor of 16 bigger, for them it's roughly 1,000 kilometers. So they have to all be within 1,000 kilometers in order to interact naturally and not notice how far apart they are. As they get the faster, or one that's 16 times faster, they have to be within 60 kilometers, and so on, 4 kilometers, etc. And if we get all the way up to one that was 16 million times faster than us, well, they have to be within a meter of each other in order to not know the difference, which means they would tend to fragment into subcultures that are separated in space. And of course, so what we would end up was having these nested circles where the center of a city would be very small, very dense, very fast things, and then farther out would be slower things that take up more space, with less of a premium on being close to things. And so we'd have this class structure reproduced in the concentric circles of a city, the concentric circles of an area. Also, the key point is that in order to interact with each other, they don't actually have to send their physical bodies around, which is what we do. So our cities are limited to a large extent in size by the time it takes us to travel across them. So commute times limit the size of our cities. Emulations don't have that limit because they aren't commuting, they're just interacting in a virtual reality, so that the amount of bits that have to be sent is far smaller than the amount of bits to send their entire selves, which means their cities can be much, much larger before congestion is ever an issue, which means they'd likely all be combined in a few relatively large cities. Perhaps 2 or 3 big cities would contain the entire emulation economy because of that lack of a congestion problem. So let's think about the kinds of lives they might live. So this, on the left, is your life. You start, then you end. Pretty simple. This is the life of someone who periodically breaks off little copies of themselves. David Brin's book, Killing People, describes a scenario like this. So you break off a copy to send them to the DMV to wait in line, and another to go to the grocery store, and another to fill out a form, etc. And then these copies end because you don't need to remember what they did. They just need to do something. And then, but that was you, and you agreed to it an hour ago, so you're okay with it, and that's how your life goes. Break off lots of copies. Another kind of scenario was in a world where you make different copies in different ways, and you're not sure which will be how successful, and you're more opportunistic, and some of them end up being successful and need more demanding, and then more copies are made of them, and others turn out to be not so useful, and then they end basically, and there's more of an unpredictable tree structure ahead of you of your life. A recursive software engineer might here make an overall design for a system of a bunch of components, then make themselves into copies, each of who works on each component, who then recursively makes designs for subcomponents, breaks themselves into copies that write each subcomponent. Then they, of course, test their components, then they test the merged components, etc., until you're back to one guy who wrote the whole thing, who only remembers writing one small part of it. Hopefully he's documented for himself, but still. Now this makes it more important to sort of design things ahead of time rather than react to things later, but that's another way you can run a life. You can do projects like that. On the right here, we have a plumber, say, who every morning gets up and is ready to do hour or 2 long plumbing tasks. They are split into, say, 1,000 or 1,000,000 copies, who then do 1,000 or 1,000,000 plumbing tasks, which all but one end. The end person did 2 hours work that day, they come home, they have a relaxed evening, they have a whole nice time, and then the next morning they're ready to do another hour's worth of work again. From their subjective memory, they hardly ever work, but of course, objectively, most of their time is spent working. It's a way of compromise to get a lot of work out of people without actually making them feel very miserable about it, which is always important. There is a natural way in which our lives have a lifespan, even when immortality is physically possible, which is that our minds become fragile. It's something that's true of lots of other systems as well. We've noticed that species and cells and products and software, a variety of systems, they become fragile naturally as they become adaptive to circumstances and they become harder to adapt to different circumstances. So, for example, if you have many descendants, they will be mostly descendants of your stem cells, your basic simple cells that start your life. And your life is going to have lots of these cells in it, but basically it's these simple stem cells that then make copies that then make other people, and then they make the simple stem cells, etc. So it's simplicity that ends up having a long, direct heritage, but it only has that because it can make this complexity that becomes well adapted to circumstances, but then it has to end. Which is another way to say that you would still be mortal. in the sense that as your mind adapted to learning how to do things to a particular world, you would become more fragilely dependent on being adapted to that. And then as the world changed, it would become easier just to take some original, simpler version of you and train it to do something else than to take the version of you that became well adapted to a particular task. Is forgetting death? So here's so as I said, usually for the ones that run fast at least, the straightforward solution to what happens when we don't need you anymore is you retire to being slower. But for the ones that are already slow, you might think, well, we can't retire to being slower because that's already still pretty expensive. So maybe they have to end. So let's take and imagine this is like someone who's awake and conscious all the time. This might be someone who pauses in being conscious. Maybe they go to sleep or are put under anesthesia and then they wake up again. This is somebody who is under anesthesia and wake up again, but now they retain the memories from an earlier point. Here's a period, maybe it was a party, they took some drug, and they don't remember anything that happened at the party. They remember before the party. Is that such a terrible life? I'm going to make a sequence of things I'm saying each step seems to be okay. Each step seems to be an improvement either. But now let's say, well, at the party we make a copy of you at the party, now there's 2 of you at the party who enjoy the party but don't remember it. Is that so bad? Well, what if now this guy that does remember the party? Well, now this is the thing where we have one guy here, we make a copy, and he laughs, and then he ends. And then we want to ask, how bad is that? You might think it's bad. The basic economic fact is some people won't think it's so bad, and they'll be the ones that make copies of it, not you. Because there is a way to look at it such that it's not so bad, and the ones who do it would be the ones who don't think it's so bad. Just like the usual Star Trek transporter, if you think the transporter kills you, you won't get into it. But fine, other people who do get into it will get around places, and people who want to hire someone to get around places, they'll hire them, and not you. That's the economist talking here, of course, right? So there are a number of issues with these copies in terms of friendships and relationships. If there's George and there's a trillion Georges, well, which one am I friends with? And which one am I supposed to be sad when it dies? And what if this George doesn't remember the great time we had together? And these are problems for basic social interactions. And so one solution to these problems is to have groups of people be copied together as a group. Groups of people where internally they have these friendships and associations, they have these relationships, so they do remember each other. And then when they end together, and so there isn't anybody else around who's too sad. There you go. Also, I expect, although I'm not that confident, that it's probably going to be typically, just like when they have identical twins, they tend to separate them at school and put them in different classes or something. People will tend to prefer that identical copies of someone not be in the same social group, and that in any one social interaction, they're just one copy of any one person. So they'll tend to avoid those sorts of duplications. Okay, another issue, however, is the idea that genders might not be equally demanded. So this is a new world of what the world wants in terms of what's productive and what's valued. That could be a world where typical male characteristics are more valued, or a world where typical female characteristics are more valued. I don't know which, but I do know that there's a problem if it's unequal, which is that we tend to like to have male-female pairs where we form long-term male-female bonds, and it's a problem if we're mismatched. If there's 5 times as many men as women or vice versa, what do we do then? Well, maybe we could all be gay, maybe we could form polygamous relationships, or I have another solution here, which is a fast-slow pair bond. So under the fast-slow pair bond, one of them is running 3 times faster than the other. This one goes through 1 cycle, and at the same time this other one goes through 3 cycles. So in the same period, one is sleeping, the other one goes through a whole day. Period working, the other one goes through a whole day, etc. But then once every day for this person, and 3 times a day for this person, and once a day for this person, they meet together and they have an hour of togetherness time, and then they're off having their lives together. So pair bonds are possible, even when there's unequal economic demand for the 2 genders of work, as long as they can be in a relationship like this. They have to get creative to solve these problems, right? Let me talk about inequality. I talked a little bit about before. So one way we can think about inequalities in terms of a power law, which has a figure alpha. A power alpha, which is greater than 1, means most of the things are small things, and there's only a few big things. When alpha is 1, it's more evenly spread across all possible sizes, and when alpha is less than 1, most of stuff is in a few big things. So, in our world today, firms tend to be spread equally across all possible sizes. Products tend to be concentrated in a few things. Cities and states also are more equally spread across sizes. Families tend to be more equally distributed, and wealth also tends to be more equally distributed. And so in our world, the richest person, Bill Gates, holds $50 billion, which is 0.02% of the world's wealth. Back in 1000, these were all pretty much more equally distributed, so over time we've seen more inequality in terms of how things are distributed. Fast forward to 2070, now what we have is that firms would probably be similarly unequally distributed, products also similarly distributed as they were before, but now because of the loss of the congestion problem, city-states would be much more concentrated rather than equally spread across sizes. Families would also be more concentrated because, again, these emulations can make lots of copies of the ones that were successful more easily. And because lifespans are now more indefinite, we expect wealth to be more unequally distributed again, because that's why firms and cities and nations are more unequally distributed. They basically have indefinite lifespans. So a city that's successful can keep growing, nothing really kills it off. Same way with a firm, but if that's a firm or a bad city, they can die off. But they are much more unequally distributed because they, in principle, have indefinite lifespans. Once the emulations have indefinite lifespans, they would also be distributed with a similar power law. And if you project that power law to a big future economy, you find the person with the most wealth may hold like 3% of the wealth. That's still 97% for everybody else, but still more inequality in wealth. There are a number of legal issues or social or sort of political issues to think about. It's logically possible for these emulations to be slaves, to be owned by other things, to be free things that take out loans, to recopy as gifts. Most of these things, differences, don't actually much matter to most of the consequences I talk about, although it might matter to you. When you try to make laws that restrict this copying, you're going to end up with a risk of black markets. So if there's a rule about not allowing to copy more, or say a minimum wage, I might be tempted to make 1,000 copies of myself in secret to start a business. And if there are, and I could undercut everybody else's costs if there were these artificially raised costs of everybody else. So in order to really raise the wages, you'll have to do a pretty draconian detection and enforcement scheme to prevent these sort of secret copies of people making copies of themselves. It would be more plausible to make the clan or the set of copies of the same original a unit of legal enforcement and politics, because it just won't do to make a copy of myself who then goes kill somebody and say, well, that wasn't me, that was him, and put him in jail. You might want to enforce the forced punishment or rules on the larger clan unit. And one of the main values in this economy are these minds that get trained, so people should be somewhat paranoid about having those minds be stolen, just like movie makers are now paranoid about having their movies be stolen, etc. People would be concerned about mind theft and be careful and have a lot of attention to cryptography. One interesting solution to mind theft will be, for some people at least, open source minds. They say, you can copy me, you got any tasks to do for me, fine, I'm up for it, you just have to, of course, pay to copy me, then I'll do whatever you wanted. Some people will be best at that, and they'll say, hey, I'm free, copy me, and I'll do your jobs. And now the wages you pay to anybody else would have to be the fact that those other people were better at something than the open source guys because they're free. All right, we can also think about some of the typical weekly activities in terms of they would probably need less sleep. But again, we're copying people who are at their physical prime and their mental prime of their life, and they're capable of working a lot. They don't need to eat physically anymore, though they might like a social process that's kind of like it. So I expect, because there's a very competitive economy here, that they would actually end up working a lot of hours, maybe up to 80 hours a week on average, which is different than our current 25, averaging over all adults in our society. But otherwise, they would still do some of the things we find important. So I'm going to stop and say, and take questions. My summary is, I'm an economist. I'm taking a scenario many people have talked about over the years, whole brain emulation. It's been science fiction. There have been other kinds of studies about it. And I'm taking it seriously as an economist to try to project the actual consequences if it were true. I'm not trying not to say anything especially original. I'm not trying to be creative. I'm trying to just say what any other social scientist would say, economists in particular, if they analyze the same things. We can make some straightforward predictions. Wages would fall, population would grow, the economy could grow very fast just because they're robots. Emulations would feel like humans, but they'd be selected, they'd be different. They wouldn't be typically humans, they'd be the humans best suited to this new world. They would work hard in an alien environment, but be okay. There would be distinct classes based on speed. Bosses would be fast, retirees would be slow. Making and copying people as teams would solve a lot of these social problems about feeling bad about other copies who don't know you or don't, or having them die, etc. And there would be a lot more inequality because of unlimited lifespans, which doesn't mean actual immortality, it means the potential for it. And in law and politics, we'd often want to use these clans of copies as a unit, and we might be somewhat obsessed with mind theft. And I look forward to your questions.
Thank you very much. We have time for question. Before you change the format this evening, we're going to have a roving microphone going around. Make sure that everybody is heard when you say your question. Please make sure you state your name, your affiliation, if you're a member or not. And with that, we'll start on that side. Okay, we have a microphone there. Yep.
John Benton, I'm a member. And my question is that my understanding is that Moore's Law is close to its end. It's running out of oomph already.
Okay, so Moore's Law is a rate at which computer technology has been improving over time. If Moore's Law changes, then the rate will change. But it's very different to say that the rate will move to stop, that the rate will be 0, or that it will be slower. So if the rate continues at some positive rate, even if it's slower, this will eventually happen just later. So the timescales would be changed. If Moore's Law ends entirely, that is, there are no more improvements in computers, then that would be a very different scenario.
Short of new technology like quantum, it likely is to come to an end, from what I have read.
So I will not present myself as an expert on that, but many people do think it will continue, and I'm following through the implications of that.
You're one person on this side.
Hi, my name is Carl Anderson. I'm not a member, but I'm an industrial designer interested. And did you happen upon any theories of consumerism or materialism as this society develops?
I'm using a set of very standard theories that predict that people are, in fact, materialistic, i.e., well, at the literal sense, they need stuff to live or they die. So this is a world of median wealth, very poor, median income, very poor. So this is a world where they would be those people would be very focused on making sure they got enough to live, enough to survive. So they would certainly be materialistic in that sense. Those who are very rich, well, it's very hard to predict what they want, but they're a small fraction, so I don't have to focus so much on them.
On that side. Al?
Well, another way where you get a different scenario, I guess, is because the way you've represented reproduction, there are no surprises, like you get from genetic mixing, for example. And that would change things a great deal. And I guess my second point goes to the no further improvement in Moore's laws, but you might want these things to be self-healing. And in that case, you are limited by natural processes, for example, diffusion of atoms to heal holes and things like that. So you couldn't go faster and faster, but you could go quite a ways in your analysis. But the lack of diversity in your reproduction would change everything compared to what we have known.
So there would be a choice of diversity here. So again, we have 7 billion people to start from. And then from those 7 billion, we can scan some, and then from those, we can make copies of them, and then we can train them differently. So we can create different diversity either by choosing from different humans or by training them differently and giving them different experiences.
Only that which you can conceive of in advance.
You can just do lots of random stuff. But the point is, there will be a choice of the amount of diversity. And in our society, we're already familiar with that. In fact, in our society, we tend to choose less diversity for the most part. That is, although we give lip service to diversity, when we're choosing people for influential jobs or prestigious positions, things like that, we tend to choose cookie-cutter people who all come from a similar social background because it tends to be easier to have a bunch of people who work together who all know how to deal with each other. So, but they would choose the optional, so I'm saying they will choose a diversity. My guess is they will choose a lot less diversity than we humans now represent. There's 7 billion of us, they might only choose 1,000 of us. That's still a diversity because you can do a lot with 1,000, but it's not 7 billion.
Al, use your mic, please. Okay. Okay, well.
I'll try to repeat the next questions if I can.
I'm Sylvia Valentine, and I'm a political scientist. What are the ramifications of some of your projections in regarding, for instance, some of the things that I've seen trying to project forward into life forms that are not really life forms? For instance, the ones and zeros in computers can now be gone through, for instance, proteins. Are they alive? Are they not? What are the social, political implications of this? Are they sentient? Are they going to be given rights?
So the question is about the social and political implications of many kinds of things being sentient or alive. I have certainly tried through most of the talk to talk about social implications of a particular kind of thing, a whole grain emulation, and what it would do socially and politically. I am explicitly assuming that this is the next big thing that happens. And I'm focused on the era after it happens, and therefore focused on, there isn't a bunch of strange aliens, and we don't revive dolphins. We don't add a bunch of strange things to the world. We're doing this one thing and seeing the consequences of this in this analysis.
So, for instance, if you want to take a look at projection of corporations, they can own property, they can so on and so
Sure.
forth. What are the kind of individual rights that you see EMS having, if at all?
So, as you know, being a political scientist, rights don't exist out in the world. They're chosen. So the question is, what rights would they choose?
Would they choose, or would they be chosen for them?
So politics is, of course, a large, complicated process, but we do know a fair number of things about politics. So one of the things you can notice about this world is it's much more driven by productivity. That is, there's a strong competitive pressure in this world where things that aren't as efficient productively just get outcompeted and don't exist. So here we can more predict what will happen from saying, well, what is efficient? What is productively efficient? So there are many kinds of rights that are cheap to give out because they don't actually cost you very much. No doubt they give out a lot of those. Rights that end up being expensive to give out by saying, well, you have the right to retire at your original full speed forever. Well, if you give out that right, that makes it very expensive to create anything because now it has this right to forever, and there'd be more of a temptation to try to evade that right in the black market. Certainly, if you're thinking about a democracy and who has how many votes, these things are running at very different speeds with very different lifespans. It would be very hard to run a democracy where they all have equal number of votes. You'll have to give proportional influence in various ways, and I think the plausible thing is just to have the clans be units, political units. So there's an internal politics of a clan that is you and all the other copies of yourself have to get together and figure out what your rules are, and likely they would be deferred to from other people. Other people say, well, just like you can run your life any way you want, we don't tell you how to say what to do about yourself. We might tell a group of copies, you figure it out among yourself, and then you tell us what you want in your negotiations with the rest of us. And there's only a few hundred clans, and politics is more feasible with negotiations among these clans.
Hi, I'm Carl Merrill. I'm a member of the society. You started the talk off with the basic assumption that the emulation of the human brain was going to serve as the basis of it. But we know there are other artificial intelligence programs that are going on, such as the one for Watson and the latest one to emulate or to simulate medical diagnoses. And it could be that we could end up with computers that far surpass anything that an emulation of a brain could do. And then it becomes almost impossible, it would seem to me, to predict what's going to happen.
So my first thing I tell you is that my primary focus is to take a scenario many people have thought is interesting technically and explore the social implications. So in that role, I am not making a prediction about which thing will happen. I'm accepting technical predictions and saying I'm going to find the social implications. I do happen to have chosen this because I think it's especially likely. I used to be an artificial intelligence researcher. I published in AI conferences 20 years ago. I published this last year in an AI conference. I've asked some people around, how far along the way till human level AI do you think we've come in the last 20 years? People who were around 20 years ago. They say 5%. At that level, you've got a long way. And of course, I also ask, any noticeable acceleration? No. So my observation of actual AI research is that the rate of improvement is very slow. If that's the way it's going to be several centuries. Or there'll be a big speed up. So that's the basis on which I say the time projections I gave here, mid-century, late century, in this century, would be before that sort of projection that I get from asking people in AI, how fast have we been improving?
When you ask a question, please stand up and speak loudly in the microphone. Make sure you're heard.
Steve Easley, I'm a member. As between the 30 selected biologics and the subsequent emulated copies, who's happier, and more importantly, why?
The 30 selected biologics.
You reduced it down. I'm not talking about
okay.
I'm not talking about the population as a whole. You've reduced it down. You take the 30, X amount of happiness. You now have your emulated copies.
Right.
X amount. Why? Or Is it X?
The robust prediction here, just like as with most biological analysis, evolution did not select animals to be happy. Evolution did not select you to be happy. Evolution created happiness as a system to direct your attention to do some things and away from other things. So evolution designed a system with a full range of happiness. That was the point. So that's one extreme. It would say, do this more, this is great, remember this. And the other extreme says, stay far away from this, never do this again. So the robust prediction is that an evolved system that's designed with those selection pressures in will again reproduce a full range of happiness. Sometimes they'll be very happy and sometimes they'll be very unhappy in order to produce them to do some things and not do others. That would be the robust prediction. I mean, they wouldn't be terribly unhappy if that made them dysfunctional. The question is, they will be roughly at the level of happiness that makes them roughly maximally productive. And hopefully that won't be too bad, but that's where it is.
Rudy?
50 years ago when Gordon Moore
Speak in the microphone, please.
Am I that better?
Yeah, much better. Thank you.
My name's Rudy Krutar. I'm a member of the society. 50 years ago when Gordon Moore came up with Moore's law, he only had 3 data points to work with. And of course you can come up with almost any law that fits 3 data points. Much more recently, I think 10, 20 years ago, Gordon Moore gave a speech at a conference and he said that Moore's law was not a law. It was a self-fulfilling prophecy. He came up with it and the silicon industry decided to base their plans on Moore's law. And anyone who was ahead of the curve could relax. Anyone behind it had to work to catch up. And that's why Moore's law appears to be solid. But it is not a law, it's a self-fulfilling prophecy.
Happy to accept that it's a trend and not a law, but it's a trend that's kept up, and it seems a reasonable basis to make some projections from. I mean, we can either stick our heads in the sand and say, you know, you can't say anything rigorous about the future, therefore nobody should ever say anything about the future, or you can take what we know and do the best you can to make projections. So I'm taking the latter camp.
Dick Jacobson, I'm a non-member. This was a fascinating talk, and I was enthralled. One of the things that struck me about it is that unless I'm mistaken, you assume that the biologics and the emulations essentially are roughly living in the same type of society. There's no difference, and it strikes me that the fate of the biologics might be very different from the fate of the emulations, who are more suited for the work that needs to be done, who can do it faster, more effectively. And so I'm just trying to think, what is going to happen to the old style humans? Because I could posit a number of scenarios that are not too happy for them.
I'd ask you, do retirees in our society live in the same society as the rest of us? Is it the same society or is it a different society? Well, in detail, the retirement village is a little different. They have different golf carts, things like that, you know. Things are going differently there, but it's still part of a larger society where they share property rights, share the same system of media and communications, share basic technology. So you could see that similarly here. To the extent they had separate needs and separate conditions that they thought best, they would segregate under those separate conditions, but they could still use the same infrastructure. They could still buy computers from the same sources. They could still use the same technology to clean things, etc.
Well, I guess my question goes more to this. Do you anticipate that the 7 billion biologics will soon be 5 billion, then 3 billion, then 150, and then they'll be living in museums after a while?
No.
Why not?
So again, the time scales here, if the world economy is doubling every week or two, then in a very short time, some things become very different. And in that time, the humans, 7 billion humans, will only have experienced another year or two of their lives. So from their point of view, nothing really has to change. They can continue experiencing their lives, and then this other economy becomes very different. And then who knows what happens then. But at least for the early period I'm looking at, there's no particular reason anything has to happen to the humans, because that's just not where the action is.
Dave Rubinowitz, I'm a member. I have a simple economics question. You're using GDP to measure the economy. And I'm wondering, how do you define GDP? First, in a pre-monetary economy, and second, in an economy that's doubling every week. And in addition, I'd like to make the comment that bosses tend not to be fast, they tend to be half-fast.
Okay. The first question was not about bosses being fast. It's about GDP. So in the initial first part of my talk, I took standard data series about GDP as it's usually defined in order to show you the charts I showed. But before a century or two ago, basically GDP tracked population. Because per capita wealth was pretty constant through history, world GDP basically tracks world population. It's only in the last century or two where there's a deviation between GDP and population. And then I'm using recent GDP statistics for that. The analysis in the rest of my talk doesn't depend on the GDP concept. I didn't use the word GDP in the rest of the talk, only in that initial data sense, only to give you an idea that there might be a new economy that would be changing much faster, but I wasn't using the concept of GDP in the rest of my analysis.
Hi. So you talk about these M's living in some kind of like virtual reality, right? And you also talk about them being motivated mostly so they'll be like paid, like the same way I'm motivated to do my job. But it seems to me that like in a virtual reality, any kind of scarcity has to be like artificial. Like when I play games, like video games, and there's like characters in there, like I can do a cheat so they have unlimited money and can buy whatever they want, right? I usually don't do it because it's not as fun. But so like in this world though, if there is scarcity, doesn't that scarcity have to be imposed by someone artificially? And if that's what's going on, is that going to create any kind of like mutual resentment?
In order to play a virtual reality game online, some computer has to be running somewhere, a real physical computer that takes real physical resources. These emulations, they're running on computers that also take real physical resources. They require hardware, they require energy, they require heat dissipation, they require repairing periodically. These emulations do not exist unless they get paid for. So the emulation, the virtual reality itself would presumably typically be much cheaper than the cost to run the emulation itself. So the hard part is getting a free hour to play. Once you have a free hour to play, you can play in lots of wonderful games that hardly cost anything relative to the free hour to play. The hard part is getting that hour when you're not working or sleeping.
One of the conspicuous characteristics of existing biologics is that they're always trying to change their minds. They're trying to adjust it with drugs or lectures or something so that so that they end up different than other people. I would think that it'd take about 1.5 minutes for these replicants to start foodling with their software. Of course. And in a week, there would be 7 billion of them.
Well, any one of them it could fiddle with itself, or others could fiddle with it to change parameters, and they would look for different parameters that had different settings that had different effects. But to make 7 billion of them, then you need 7 billion more real physical resources. So taking any one copy and fiddling with it is relatively cheap, unless you're the copy and you're worried about what will happen to you. But making many more of them is expensive, so it costs real resources to make more of them. No doubt initially one of the first things they'll do is they'll try to play with these. They'll twiddle knobs on these simulations and see what happens when we twiddle all the knobs. They'll try to find settings that make you happy, that make you productive, focused, distracted, whatever else. They'll find all those things and they'll figure out, well, what sort of task does that well match to? And they will tend to make ones whose knobs are set for the task that you're doing. But the initial assumption is these are mostly opaque, so that quickly runs out. You've got some settings, you can run them, but now you've got a black box and you can make more copies of it, but it costs more resources to make more copies. And in order to do that, you need to get some real money to get some copies.
So that side, go ahead.
Thomas McCaskill, member. I was interested in your wealth distribution functions. You had 3 of them there. And it looked like to me that, okay, back before the industrial age, we had close to a uniform distribution. And then, of course, after the industrial age, it began to change. But it looks like our current distribution function is not a unimodal, but it's, I would call it bimodal. And that is, you got a whole lot of the density down about the minimum wage part. And then we've lost our middle class. You know, I mean, normally that's good news, lose the middle class, and then at the very tail end, you got a second peak, so it's really...
We actually have a lot of data.
Now, give me a chance. Do you remember Henry Ford? How do we get out of this thing? In other words, the reason that Henry raised the wages of his workers was so they'd have more money to buy his cars, and then maybe if some of these people, you know, would pay, a lot of us to do these very diverse and interesting things, maybe that would generate more wealth.
These numbers I'm showing here are based on large data sets where people have looked at the distribution of firm sizes, city sizes, nation sizes, distribution of wealth, distribution of families. These numbers I'm giving you are actual power law fits to those things. For none of these distributions is it bimodal. They are all unimodal distributions. And it's just not true that Henry Ford gave money to his employees so they would buy more cars. He gave it so that they would stop leaving work and stay at his job. They had a big problem that people would stay on one job for a short time, leave, and then the new person you got was not very well adapted to the job. They had to keep being retrained. So he did it for worker retention and not for getting, he was happy that if they bought the cars with it, and he may have actually required they spend some of the money on cars, but way of getting some of the money back.
Hi there, my name is Rahul Sinha. I'm not a member. My question is, I realize your analysis doesn't encompass this, but what is your opinion on restraint of trade or restraint of activity because of incumbency? Whether it's biologics restraining the scope of the EMSs as a result of threat from competitive pressures, or the initial EMs when capacity is limited for the system, as the system expands, preventing clones because they want more resources for themselves.
So I am an inheritor of a vast tradition of economics, and I'm happy to just be a representative of that tradition in this context. I'm not trying to be creative. I'm not trying to make up new ways of doing things. I'm just trying to tell you how we do it as usual in economics. Our usual approach is that first we analyze the supply and demand scenario to see what happens then. Then we look for what we call market failures, way in which the supply and demand scenario doesn't actually apply very well. And then we think about possible interventions that might reduce those market failures, or at least analyze how they might increase them too. So our usual analytical framework is to identify market failures and then think about interventions, restraints of trade, taxes, subsidies, etc., ways that might adjust the system to reduce those market failures. You can apply all those tools here. It's straightforward to do so. We have a rich literature on how to do all of these things, and it isn't necessarily that much different here than it is in the usual cases. We've got a literature on what's called industrial organization, all about in industries when there are a limited number of firms, how they might compete differently from simple supply and demand, how that might make things inefficient, and how you might want to do things different to improve that. And it was straightforward to apply that all here. I hope I can start a tradition of many people doing analyses here, but the first effort is to just do the first cut. To do the simple, standard, straightforward thing we're all supposed to do as the first step in these analyses, and that's what I've tried to do here.
Do you have two more questions? Go ahead.
I'm Eric Alving. I'm a member. And it's interesting that you look at apparently money and gross national product and things like that. And I don't think that's what really drives most people. When you give people 100,000 or 200,000 a year, they're happy and they look for other things. But aside from that, this brain simulation that you talk about has a flaw, because if you take the brain by itself, it doesn't do all the things that we do. We have a body, and we have feedback from our body. We have vision and sight and hearing and feedback from that, and we do something and we get feedback from our senses. So either these robots have completely emulated human beings, in which case they are human, or they're not, and if they're not, in what way are they not?
So, you have a body, you are in an environment. In some sense, any part of the environment changes, that affects you and it makes you a little different. The question is how different and how much do you care? People play video games in visual environments that are not just like the physical real world, because they try to make it easier to compute. But people often enjoy those video games, and they often are functional in those video games and able to do things in those video games, even though they are not just like the real world, but they are much easier to compute. We know so much about how to emulate bodies that we mostly don't talk about that here, because it's pretty straightforward that if you can go to all the trouble to emulate a brain, emulating the relevant parts of the body is just vastly easier, and you can do that too. But you wouldn't necessarily emulate an exactly human body. You might emulate other bodies because you wanted other things done. You want someone to run a steam shuttle, maybe the steam shuttle becomes their body. Maybe they don't necessarily have arms and legs like we do. We already actually can go a long way taking things like a car and projecting it into our mind and making it feel like it's our body. We have this body, but we often run other kinds of machines by projecting them as if they were part of our body. So emulations, it's all the more easy to make them actually their body. They could have a range of bodies, and the human mind is flexible enough to become something in that context. It is not the same thing it was with the body like yours exactly, but how much different do they care? I mean, the point is, the economic pressures are defined versions of these emulations that do particular tasks. How much they are like the originals is just not very much a concern. Your original comment was about we have lots of other motivations, and how much these other motivations affect our behavior depends a lot on how rich we are. The vast majority of animals through history have been poor enough that their behavior was molded by the basic necessities of functioning in their environment and not surviving. That was true for most humans until very recently too. Humans were animals well adapted to their environment, where their behavior evolved to be functional and help them survive and not die and reproduce and things like that. It's only very recently, in the last 200 years, where we have suddenly become so rich that we can afford to do things that are not especially functional, but we can afford to do them anyway, and we choose to do them anyway, and to heck with being functional, because it's what we want. This is what I've called the dream time, this rare era in history, where there was a lot of flexibility, a lot of things were possible. We could follow intuitions that weren't very functional, but this dream time will end, and the future will go back to the way it's almost always been. Creatures well adapted to their environment, where the kinds of things they do make sense in terms of what it takes to survive and thrive in their world.
Last question.
Craig Yan, I'm not a member. You seem to believe that the increase of the computation would help you to emulate the brain, but a lot of that is software. For example, intuition, free will, adaptability. All those things are key for creating things. We can have rules then we can load into the robot, but what about robots themselves creating rules?
So all of the things you talk about are features of people, and they exist in people because people have brains, and brains have a particular structure and a particular design that produces particular computation in brains. That's how all those things happen. The idea here is to make a copy of a brain in terms of how it's connected software-wise and turn that on and have it be able to do all those same things. Not to try to understand why it happens, but just to make a copy. In the same way, if your friend saw a movie that they liked, they can show you that movie by making a copy of the movie file. They don't have to explain to you exactly why that movie makes you feel one way or another or why you like it. They just make a copy of the movie file. Then you run that new copy of the movie file, and then you can experience the same movie.
Okay, but if a person that, say, sometimes he's creative, sometimes he's depressed, sometimes those other emotions, you can copy him at the wrong time. You made the wrong copy.
Well, then we won't do that. We will be selective about what we copy and how we change. That's the whole point. We'll be very selective, and not a random sample of people and random human moments, the most productive, useful, well-adapted people and moments.
I know there are many more questions, but the speaker will be around through the social hours, so you have the opportunity to ask him on a one-to-one basis. Thank you very much for... We have two presents for you. This is the announcement of the lecture, framed and signed by the members of the General Committee. It's for you to keep.
Thank you very much. I'm honored.
You're welcome. And secondly, today was the DuPont Summit, so Paul Rich, the sponsor of the lecture, would like to offer you a medal commemorating the event.
Thank you.
Thank you very much. As I mentioned, the speaker will be around for the social hours, so give the opportunity to ask the questions. I know several of you have a lot of questions, a very exciting subject, maybe controversial even, but that's good. We like to have questions. So thank you for sticking around to answer more questions. Thank you. So before we retire to the social hour, I'll have some housekeeping items. If you dine with us this evening and have not settled your account yet, please see our treasurer, Bill Maish. Bill in the back. Thank you. As always, appreciate your dues and contributions to the society. The society is a tax-exempt Section 501c3 organization, and your contributions are tax deductible. If you're not a member of the society, you'd like to become a member, and of course, you receive announcements and dine with the speaker before the lecture. You can go to the website. It's a simple application form, and typically the turnaround time is very quick, within a couple of weeks or so until the following meeting. So get approved, hopefully, to become a member. So please go ahead and do that. We appreciate new members, particularly the younger folks, and I see a lot of young people this evening here, which is good news. Also, I'd like to remind you that, particularly to the members, only 1/3 of the contributions come from membership. The other 2/3 come from essentially the generosity of the members through additional funds to the operational trust, or the operational fund rather, as well as to sponsorship. So if you're interested to sponsor a lecture or a portion of a lecture, see any of us and we'll tell you how to do that. It's a very simple process. And of course, we appreciate always becoming a member, as I mentioned. Out of curiosity, I see a lot of, how many people are first this evening to this? You can raise your hand, how many people are the first time at this event? So quite a lot, I guess, almost 20 or more, so it's very good. Hope to see you again at the next lecture. Our next lecture is 2009. It will be held on December 14th, which is a week from today. We have to move the lecture 1 week earlier because of the holidays to make sure that people are still in town. And that will be the last lecture in this calendar year. The speaker is Robert Deans. Is Executive Vice President of Regenerative Medicine, Athersys Incorporated and Regenesis BVBA, and his lecture is entitled Stem Cells, Challenge in Clinical Applications. So go from economics to bioscience in a week or so. I'd also like to mention for those who came today, the non-members, the club has a certain policy about dressing code, I suppose. So if you leave, make sure you leave from the side door or come in the side door, you come back again, unless you're dressed up. Your coat and tie, that's a policy. So I would appreciate if you follow the rule because somebody may object to that. So appreciate if you follow the rule of the club. I have no other announcements to make. Is there any further business of the society? If there are no further business, I entertain a motion from a member to adjourn the meeting.